It's time to begin a discussion on work and kinetic energy and how they're related to each other. We're going to begin our discussion talking about work. At the end of this lecture, or series of lectures, you should be able to calculate the amount of work done by various forces. We'll pick some really specific forces, and that'll give you an idea of how to do it for other forces besides those that we choose. You'll see the definition of work requires a discussion of the dot product, and so we're going to revisit that dot product that we talked about when we discussed vectors some time ago. The concept of work also involves integration, and so our calculus is going to come into play. And then we'll define kinetic energy, and we'll look at the relationship between work and kinetic energy, and we'll use that relationship to solve some problems. And then finally we'll calculate power and efficiency. So we'll look at work as the amount of energy transferred to or from an object by means of a force acting on the object. And we'll look at the signs of that work as well, and if there's energy transferred to the object, then that amount of work is positive as far as the object is concerned. And if energy is taken away from that object, then the amount of work done on that object will be negative. So the work done by a force and the work done on an object, those are going to be terms that we're going to want to look at very carefully. So this is how we define work, and the subscripts 1 to 2 indicates that something is happening from a position 1 to a position 2. In physics we use the letter W for work, but in engineering oftentimes they'll use the letter U for work, so be careful of that letter change. So we define the work, hence we use the 3 equal signs because this is a definition. And the integration says the work done by a force, F, in moving from position 1 to position 2. And we're going to integrate that force over that change in position. Now you'll notice a couple of things. First off, force is a vector quantity. Secondly, dr, which is the displacement, but it's a very infinitely small displacement because this is an integration process. Both of those are vector quantities. But when we go to calculate work, we use the dot product of those two vector quantities. And so in the end, work is a scalar quantity. So you'll notice over here, there's no vector sign above the W. So work is a scalar quantity, and it's going to be related though to the dot product of two vector quantities. So if I look at the units involved in here, force is in the unit of newtons in the metric system, and displacement is in the unit of meters in the metric system. And so work is Newton meters, and this is often referred to as the joule, named after a physicist, Joule. And we're going to use the capital letter J for the shorthand for the number of joules. So we can either use Newton meters or we can use joules. Both of them will be used equally often. In the English system, force is in pounds and distance is in feet. And so the pound-foot or the foot-pound, and the foot-pound is used for something else we'll see later on. So is the Newton meter. So we've got to be really careful about our units. But the pound-foot or the foot-pound would also be legitimate units for work done. But that's in the English system and not the metric system. So let's take a quick look at the work done by a couple of forces. This is just a relatively simple example. So let's assume that I'm pushing on a box with a force of 100 newtons. So there I am pushing on this box. There's a gravitational force acting on the box, there's a normal force acting on the box, there's a frictional force acting on the box. And the box is going to start 13 meters away from some origin, and we're going to end up 78 meters away from that same origin. And what I'm interested in are two things. First off, the work that I do, and secondly, the work done by gravity. Now, we could find the work done by the normal force and the frictional force as well. But for right now, let's just concern ourselves with these two values. So I'm exerting a force of 100 newtons in the I direction, and so the x-axis is clearly in that direction. And the displacement is 78 meters minus 13 meters. In other words, my initial position is 13 meters, my final position is 78 meters, and so dr, let's keep in mind the force is constant, it's going to come out of the integral, dr is 78 minus 13 meters in the I direction. And so I have 100 newtons in the I direction, 65 meters in the I direction, and when I multiply those out I get 6,500 newton meters. I dot I is equal to 1, so this is not I hat. There's no vector quantity there. Work is a scalar quantity, but it's 6,500 newton meters. Gravity, on the other hand, you'll see here we define the gravitational force as 200 newtons. Gravity is in the negative J direction. The displacement is still 65 meters in the I direction. And so when I go to calculate out the work done by gravity, I'm going to get 0. And the reason for that is that the j dot I value is 0. That is to say, the dot product between two vectors which are perpendicular is equal to 0. So gravity does no work on this object. Doesn't mean the force of gravity isn't there. Simply in the displacement from 13 meters to 78 meters, no work is done by gravity. There is still work done by me, and if we calculated it out, there would be work done by friction. But no work is done by gravity. In a similar fashion, no work is done by the normal force, because it's also in the j direction. Now, you really need to be careful of the dot product, so let me remind you of a couple of things. Let's assume the force is in this direction, and the displacement is in that direction. I'm just going to put delta r here for the displacement. Then there's an angle between the force and the displacement. We'll define that angle as theta. And so the work done here, and I'm going to actually call this delta W because it's the work done over this displacement delta r. The work is equal to the force dotted with the displacement. But as you recall from dot products, that's equal to the magnitude of the force. So notice I don't have a vector sign above that again. The magnitude of the displacement, again no vector sign, and the cosine of the angle in between. Another way to look at that, if I drop a perpendicular from the force down to r, then there are two components to the force. This one I'm going to call F parallel. And let me define that then. F parallel is the component of the force F parallel to the displacement delta r. There's another component here. I'll call that F perpendicular. And that is the component of the force vector F perpendicular to the displacement vector delta r. Now in the case of cosine theta, the cosine of theta is equal to F parallel divided by the magnitude of the force F. So this side has a magnitude of F. And so F cosine theta equals F parallel. Given that, I can write the work then as F parallel times delta r, because here's F, here's cosine theta, and that's F parallel. So the work is equal to the component of the force parallel to the displacement times the displacement. Given those same two vectors, angle theta here, some force F there, delta r here, I could extend F out here, and then I could drop a component delta r perpendicular to F, and so I could label this blue vector as delta r parallel and this as delta r perpendicular. And in this case, delta r parallel is the component of the displacement delta r parallel to the force vector F, and delta r perpendicular is the component of the displacement delta r perpendicular to the force vector F. In this case then, delta W is still equal to F delta r cosine theta, but the cosine of theta equals delta r parallel divided by delta r. And so delta r cosine theta equals delta r parallel. And so the work done is equal to the force times the component of the displacement parallel to the force. So sometimes it's going to be easier to calculate the component of the displacement, and sometimes it's going to be easier to calculate the component of the force. And we'll see some of that yet before this is all said and done. So here's a little example. I have a child pulling a little red wagon, and she's pulling on the wagon with a force of 25 newtons, and the angle of that force is 53.1 degrees above the horizontal. So how much work does the child do when she pulls the wagon a distance of 10 meters? And so the displacement of this wagon is going to be to the right, a distance of 10 meters. And so delta r is equal to 10 meters. That's a vector quantity in the I hat direction. The force is equal to 25 newtons at an angle of 53.1 degrees above the positive x-axis, in this case the horizontal. And so I can break this down into 25 newtons times the cosine of 53.1 degrees, I hat, plus 25 newtons times the sine of 53.1 degrees, j hat. And that turns out to be 15 newtons in the I direction plus 20 newtons in the j direction. I'll remind you that triangle, as we use a lot, this is a 3, 4, 5 triangle, and that angle between the 3 and the 5 is just 53.1 degrees. The angle here between the 4 and the 5 is 36.9 degrees. Those are angles that we'll use quite often. And so the work done by the child is equal to F dot delta R. But that's going to be 15 newtons in the I plus 20 newtons in the J, dotted with 10 meters in the I plus no meters, 0 meters in the J. And so recall again from dot products, you take the I component times the I component. So 15 newtons times 10 meters, those are the I components of each vector, plus 20 newtons times 0 meters, that's the J components of both vectors. This of course is 0, and so I'm left with 150 Newton meters. And so that's the work done by the child. So there may be other forces at work here. Perhaps there's a frictional force or somebody pulling back on the wagon. But the question is only looking for the work done by the child. And so that's the only force we concern ourselves with at this time. You might also have looked at the fact that this is 15 newtons parallel to the displacement of 10 meters. And so the work done would be equal to the force component parallel to the displacement, that's 15 newtons, times the displacement, that's 10 meters. And again, I'll get 150 Newton meters or 150 joules. So either of those methods will work. A component of the displacement parallel to the force is doable, but it doesn't make any sense. So we won't look at it for this problem. So we've already looked a little bit at the work done by a constant force, but let's just look at that a little more formally then. So the work is equal to the integral from position 1 to position 2 of the force vector dotted with the displacement vector. But if the force is constant, it comes out of the integral. And so this is force dotted with the integral of the displacement dr, integrating from r1 to r2. But when I integrate just the integral of dr, there's still my force vector, I get the displacement delta r from r1 to r2. These are all vector quantities. And so this is just equal to F dotted with r2 minus r1, vector, vector, not the dot product. And so that would be the work done by a constant force going from r2 to r1. And this is a common enough situation that we wanted to bring it out, and we'll look at it again.